All right, welcome back. We were talking about linear transformation. In example 2.1.4, here's the question. For which value or values of n would the following function be a linear transformation? And the function sends an n by n matrix to the determinant of A. All right, this seems like a tricky question because it looks from the question that for certain n it would be and for certain n it wouldn't be. All right, so let's try to prove that it is and we'll see where we get in trouble. All right, so let A1, A2 be in n plus n, and let K be in R. All right, so first property that I have to look at is K times A1. I need to apply T to that, so that's determinant of K times A1. Don't know if you remember this, but when you take K out of the determinant, you need to take it out of every single row. So you take it out n times, and so what you get is K to the n determinant of A1. But what I want, so this is to be compared to K times T of A1, that's K times determinant of A1. These don't look like the same things. Unless n is 1, and that's probably why the phrasing was there. All right, so let's try to prove that for n not 1, it wouldn't be a linear transformation, and that for n equals 1, then it might be. All right, so case number 1. N is bigger equal to 2. Let's take K to be, 3. Then T of 3. And let's take A to be something specific as well. And let's take A1 to be the identity. Then T of KA1 is K to the n determinant of A1. That's 3 to the n. And then K times T of A1, that would be K times determinant of A1. That would be 3. And these are different because K is bigger equal, N is bigger equal to 2. All right, so T is not linear. In fact, it doesn't preserve the sum either, right? A determinant of a sum, that was weird too, if you remember from linear 1. But now let's look at our, I don't know if I'd call it a bummer case. Let's look at what happens for n equals 1. Let's look at this map for n equals 1. We're talking about 1 by 1 matrices. So it's T from M1 cross 1 to R. It's going to send a matrix A, which looks like this, to its determinant. And that's just A. And so you can see it's a much more simple and natural map here. I'm just sending a 1 by 1 matrix to its lone entry. So it's going to be nice. So let's prove that this is linear. So T of KA, that's T of K times A, and that's KA, which is K times T of A. Yeah, so in that case, it's almost silly. They look identical. And then T of A1 plus A2, that would be T of A1 plus A2, let's say. And so I'm going to get T of A1 plus A2. That's A1 plus A2, which is T of A1 plus T of A2. And so yes, for n equals 1, T is linear. That's a good problem. All right, so let's look at one final thing at proposition 2.1.1. This you'll prove in the worksheet. I just wanted it to be in your notes. Let V be any vector in Rn, so En is Rn with the usual operation. The function that sends W to the projection of W onto V, if you remember the formula, that function is a linear transformation. So let's write the formula. That's W dot V over length of V squared, and all of this is a scalar, and you multiply it by V. All right, so this is a linear transformation.